In this video, I'll talk through the 2021 Advanced Higher Chemistry paper. I'll explain how I would approach each question. Starting off with question number 1, we first need to know which order the orbitals will fill in. Next, we need to check how many electrons potassium has. You can get this from either its atomic number or from its electron arrangement in the data booklet. We have 19 electrons in total. We have 18 electrons to fill up. That means we're going to have 1s2, 2s2, 2p6, ps2. That takes us up to 12 at the moment. Next, after the ps comes the 3p. We can get a maximum of 6, and those 3, 6, that takes us up to 18, meaning that our last electron is going to be in the 4s1 orbital, and that gives us a correct answer of C. Other option, since potassium is in group 1, is part of our S block. We have our other blocks shown on this image. For question 2, we need to be aware of the different quantum numbers we need to know. Oxygen has 8 electrons. This means its arrangement will be 1s2, 2p6. The question is looking for a quantum number that is not possible for a 2p6 electron. First quantum number to consider is the principal quantum number. We have 2p, therefore our principal quantum number is 2. This gives us 2 options for our angular momentum quantum number. If we have a value of 0, this means it will be an s orbital. The one that we care about is a p orbital, which means its value of L would be 1. Value of L of 1 means that we're dealing with a p orbital. We're dealing with our ML. That's the different possibilities of the orbitals, which we have 3 of them. Value of L equal to 0 would mean this would be an s orbital. We are asked about a p orbital for oxygen, making A our answer because it's not a possible value for oxygen's outer electrons. Moving on to our next question, we're asked about the unpaired electrons in chromium. Check how many electrons chromium has. Chromium is hiding. There we go. Got 24 electrons. At this point here, chromium is one of our exceptions. This means that it doesn't quite follow the fill-in process that we've talked about before. We'll start off as if it would. 1s2, 2s2, 2p6, ps2, 6, 4s2, up to our 3. But at this point we've got 10, 20 electrons. That means we need 4 in our D shell, or 3D shell. If we have a look at these as a box notation, we have this as a box notation. End up with electrons here. 3D, there's 5 boxes to put in. So we would end up our electrons, they would singly fill it first. There. With this one, what we would have is we have a full 4s, and then our 3D is not half filled or filled. Nothing really special or nothing particularly stable about it. What would actually happen to increase the stability? In order to increase stability, there would actually be 1 electron in the 4s, and we'd have another electron in the 3D. This would leave us with 4s1, 3d5 at the end. This then gives us 6 unpaired electrons, which gives us an answer of E. If we were going off of the one that follows Aufbau's principles exactly, we would end up with just the 4 of them, but it has that special stability. Copper is in a similar scenario where the electrons would be arranged in such a way to maximize stability. On to question number 4, we're asked about Ka, the dissociation constant. So the higher the dissociation constant, the more acidic that we've got. This means that our Z would be most acidic, and then X would be the least acidic. If you wanted to think of it in terms of how basic it is, X would be the most basic, and Z would be the least. In our questions, X is less basic than Y. That's incorrect. X is more acidic than Z. Also incorrect. Y is more basic than Z. Sounds good to me. Y is less acidic than X is incorrect. The higher Ka, the more acidic it will be. Next one. Asked to calculate the standard 3 energy change in kilojoules per mole. First, we're going to identify which equation matches which part of our target equation. Carbon solid is in equation 1, but we only need half of it because there's only one carbon we're needing. So that's going to give us half of delta G1. The zinc oxide is on the wrong side, which means that's going to have to be negative. We're only going to take half of it because we only want one zinc, and in delta G2 there is 2 zinc oxides. So let's make that half of delta G2. Next up, we'll pop our numbers in. So we're going to have half of minus 475. Take away half of minus 340. That's going to give us minus 237.5. Add on 170. That'll give an answer of minus 67.5. Makes our answer A. Watch out for the fact that this is the equation that we are trying to make, which means when we're comparing it, we want to bring our values down to give us just 1 mole of each of them. Next one, we're talking about the enthalpy of formation. We want 1 mole of a substance being formed from its elements in their standard state. First of all, I'm spotting that we're making 2 moles of carbon monoxide and hydrogen bromide. Therefore, this will not be an enthalpy of formation. Get rid of them. Next, I'm looking for the state at which the elements exist in. We have magnesium solid and oxygen gas and making magnesium oxide. That works. That is then therefore correct. Problem with D is the bromine. Bromine is one of 2 elements along with mercury that appear as liquids at room temperature, making it not the standard state, which means that is incorrect answer. If you're unsure of what state an element would be in at room temperature, we can look at the melting points and boiling points. Room temperatures, talking around about 20-25 degrees. That is above the melting point of bromine, meaning it has melted into liquid. It's below the boiling point of 59, which means it's melted but not turned into gas. Therefore, we're going to have a liquid for bromine. In this question, we're asked to determine the order of reaction for each reactant. We need to decide which 2 experiments we should compare. We're looking for the combinations where there's only one difference in the concentrations. I'm looking for something that will deal with the BrO3-. I'm looking at which 2 equations have that as the only difference, just 1 and 2. Look at equation 1 and 2. We have doubled the concentration. If you look over to the side, we have doubled the rate. If you double the concentration, it doubles the rate. That means it's going to be first order with respect to that reactant. Goes out D. Next one, we're going to be trying to compare for the bromine. For 1, where the only difference that. If we go for 2 and 3, that's the only difference there. We double the rate, and again, we're doubling the concentration, meaning again, it's going to be first order. Respect to that chemical. Moving on, we're dealing with the hydrogens now. I'm looking for 1 and 4. The only difference is the concentration of hydrogen ions. When we compare these 2, what we should notice is that, well, if we doubled, we would get 1.6 times 10 to the minus 4. But we've actually got 3.2 times 10 minus 3. This means that we have quadrupled our rate. And if you quadruple the rate, this means that it is second order with respect to the hydrogen. That puts us at an answer of B. You're looking at how does the concentration of the reactant affect the rate. Moving on to number 8. If we have a 0 order reaction, this means that the concentration of that chemical has no effect on rate. To answer this question, we need to check what each axis is representing in our graphs. Our top 2 are to do with rate and concentration. 0 order, it will have no effect on the rate. That would have given us a graph that's just a straight line across. That means that A and B are incorrect. Next up, For C, we do have that line going across, which if the graph was to do with concentration and rate, it would be correct. However, it's concentration and time. And that rules that one out. Reason that D is correct is it will not speed up the rate of reaction, but it will get used up over time. So over time, the concentration of the reactants will decrease, and that's why D is right. So always check what the labels are, so you know what the graph is supposed to be representing. On to question number 9. When we're given a rate equation, this tells us the parts that are involved in the slowest step. That means that our slow step has to have 2 P's and 1 Q. That's in our slow step. If we look at A, it's got 1 P and 2 Q's in the slow step. That one is incorrect. We have 2 P's and 1 Q. That's looking good so far. Let's check the other ones. We've got 1 P and 2 Q's in our fast step, 1 X and 1 P in the slow step. So that is incorrect. Then fast step we don't really care about. Slow step would be X and Q. Then that's incorrect. B is the correct answer. The rate equation represents this slow step in the reaction. Next up, we are asked about nucleophiles and electrophiles. We have got something that is negatively charged. This will be attracted to positive charges. Nucleus, which contains the protons, is going to be positively charged. Therefore, this will be a nucleophile because it's attracted to the positive charged parts of a compound. That rules out these two. Next, we have to say if we've got a primary, secondary, or tertiary alcohol. We need to focus on the carbon attached to the OH group, the hydroxyl group. This has 2 other carbons attached to it, making it a secondary alcohol, making A our correct answer for this question. Moving on to question number 11, talking about homolytic fission. Homo is to do with things being the same, and lytic is to do with splitting. When we have homolytic fission, that means that 1 electron goes to each atom in the bond. This will produce radicals which have unpaired electrons. Most commonly happens when you have non-polar bonds. Something like bromine would be highly susceptible to this happening. That gives us our answer of B for that one. If you were breaking and making ions and things like that, that's then going to be your heterolytic fission. Moving on to talking about sigma and pi bonds. Sigma bonds are the first bonds made. A couple of approaches we can take. First one is to think about the functional groups involved in each of these chemicals. We have carbon-to-carbon single bond, carbon-to-carbon double bond, carbon-to-carbon triple bond, and we have a ring. When you have multiple bonds, this will reduce the number of hydrogens that can join onto the hydrocarbon. Because of that fact, then with your hexyne, that's going to have less single bonds with hydrogens because more of the bonds are taken up with the triple bond. When you add a carbon-to-carbon double bond, you need to lose 2 of the hydrogens because carbon can only make 4 bonds. If you put in a triple bond between carbons, you're again going to have to lose hydrogens. Each of the bonds that joins on from a carbon to hydrogen will be a sigma bond. Therefore, the triple bond will have less hydrogens and therefore less sigma bonds, making our alkyne our correct answer. Moving on to our next question, we're asked about an addition reaction where the double, or in this case triple bond, is going to break. We're going to add on hydrogen chloride. The parts on the left of the molecule will stay as is. This time we're going to take our carbon, we're going to break one of the triple bond, make that into double bond. This is going to allow us to have 2 new bonds that's going to be present. We have a hydrogen and we have a chlorine to add. Markovnikov rule says that the hydrogen will join to the carbon with more hydrogens already. Another way we could say it is that the hydrogens will follow hydrogens. This means that our hydrogen has to go on the right hand carbon, and and our chlorine would end up on the middle carbon in here. This means that the number in front of it is going to be a 2, not a 1. The reason it's going to be propene, not propane, is if I was to break the double bond and I have just a single bond here, we would need to use more hydrogens and chlorines. So we would end up with a molecule that has 2 chlorines attached to it. So it'd be dichloro, which is not what we've got here. We're just adding the 1 chlorine and 1 hydrogen, breaking one of the bonds in the triple bond. That gives you your answer of 2-chloropropene, which is D. Next question, next one. Got a condensation reaction. We need to try and figure out how this is going to come together. The most typical condensation reaction that you would have came across is when we have an alcohol and carboxylic acid. When these join up and form our ester, water is also produced. The definition for a condensation reaction: 2 molecules joining together and a small molecule, usually water, is formed. When we look at what we've got here, we've not got a carboxylic acid. We've got a chlorine on the end where in a carboxylic acid, it would have been OH. We're going to lose this chlorine. We're going to lose the hydrogen off of the alcohol group, the hydroxyl. That means that we're going to not make water, but we'll make HCl. In terms of how these join up, we'd redraw it, pointing the functional groups at each other. That might assist us. After these 2 atoms are lost, we're going to have a bond forming between the carbon, double bond O and O. We then need to look for whichever answer matches this up best as possible. Here we've got branches involved on either side. We have got our carbon double bonded O, maybe this carbon here and this carbon here. This would make part of the main chain, which means we would not want to have brackets for the left hand side. Because this molecule, when it joins up, we've kind of rotated it round so it's up on its side. This means that we are going to have our branches represented in the brackets, making C our correct answer. So it's not just about what happens, as in hydrogen and chlorine come off and we put them together. It's how they will arrange together and join up as we go through. Here we've got secondary amines forming new chemicals reacting with some carbonyl compounds, and we need to try and follow what's happening going from left to right, and we need to try and figure out which carbonyl compound would react with the chemical given to form this new type of chemical called an N-amine. First thing I'm noticing is that the way they've arranged them is different, trying to catch us out, because we've got our N-C bond going here horizontally, whereas here we've got it going vertically. We need to try and label it up following the pattern that says above. This means that the ones coming off of the nitrogens are going to be R, E, and R4. That means that when we go down to the bottom, this one is going to be our R1. This one is going to be our R2. As we track it back, we care about the carbonyl compound that we've got to begin with. That means I'm going to ignore the nitrogen parts, because that came from the amine that reacted with it. I'm going to focus on parts that's left. When we look at what changes going from left to right, well, we had 2 carbons, and then we had our R groups. Again, we've got our 2 carbons, and then we've got our R group. So what I'm going to have to do is off the carbon at the top, so I'm going to say that's the one that's beside R1. I'm going to need to make that a double bond to an O. We have double bond and O. We've then got our R1 group, which is a CH3. When we're writing it, let's make sure we put it with the C first. Got H3. Connect it through the carbons. Next, we've then got a CH2. Then connects to our other branch. Here we've got 4 carbons in a row, which makes it bute, ruling out the top 2. The C double bond O, the carbonyl group, is on the second carbon. That makes it a ketone, not an aldehyde, making our answer D. You're trying to follow what they're doing, mark it up as you go, and we get our answer of D for that one. Next one, talking about different functional groups. Well, a carbonyl group, we have C double bond O, carboxyl, we want C double bond O, then OH. Hydroxyl is an OH, then phenyl we're looking for benzene ring. Stands out to me first is the benzene ring, the phenol ring. We have just an OH here sitting there. Thing you need to watch out for is, yes, we have a carbon double bonded O. There is no OH connected to that carbon, which means it's not a carboxyl group, but it is a carbonyl group. Up to here looks quite similar to the C double bond O. OH would need to be on the end there. That's not. This is an ester link. They're quite easy to get mixed up. Just you're looking for the COOH rather than just COO, making our answer of the one that's not present is going to be a carboxyl group for that one. Moving down to question 17. Here we're looking for our different environments that we would have. First thing we're looking for is, can we pair off any sets of hydrogens that are flanked by the same things on each side? So what I mean by that is this one here has got an oxygen beside it and a CH3. That is equally true for this. This means that this will be one environment. The second environment we've got the CH3s because they are beside CH2 reduction after that as well. That means we'll get two environments, which get rid of two answers. Next, we're using the N+1 rule. That means that when we look at the particular environment, we look at how many carbons are adjacent. In this case, we've got 3 carbons adjacent. We add on 1. This means that that will be shown up as a quartet. This is 4. We have then, if we're focusing on the CH3 part, that is beside 2 carbons. That means that that's going to give rise to a triplet. Makes our answer A. We have a triplet and a quartet. That's the N+1 rule. Look at how many hydrogens are in the surrounding carbons, then add on 1. That gives you your splitting pattern. Next one, we're looking for the lowest boiling point present. In these ones, I would just focus in on the NH parts. That's what would give rise to hydrogen bonding. We're looking for the one that doesn't have hydrogen bonding because hydrogen bonding would increase the boiling point. For hydrogen bonding, you need hydrogen directly bonded to fluorine, oxygen, or nitrogen. We have NH2, that means we do have N to H. That means that would have hydrogen bonding. Similarly, we have an NH bond here. That one out. Next one, we have got, again, a nitrogen to hydrogen. They all would have hydrogen bonding, whereas we've just got nitrogen surrounded by carbons, which make our answer C. Your other option for how to tell which one would have the lowest ones is that tertiary amines would have lower boiling points than primary or secondary. C is tertiary, and that's our one with the lowest boiling point. On to number 19. This one we're trying to prepare ethane by adding iodomethane to sodium. Try to look at what's happening here. What have we got? We've got our methane part, iodine. So we're losing the iodine, which is joining on with the sodium. And then the two carbons are joining together to make ethane in this case. What this question is saying is that we're using a mixture of different compounds. We're trying to work out what we'd be able to produce. We had the iodomethane plus iodomethane, like the example they give us, then we're going to make ethane. We could also take iodoethane and react it with another iodoethane. Then here you're going to end up with 4 carbons joined together, because here you took each of the single carbons and put them together. So that would make butane. And the other option would be to use one of each. So use iodomethane plus iodoethane. That time you're going to have 3 carbons, so that's going to make propane. So you get your all 3 possibilities here, and that's what you'd get from that. See, you cannot get methane because we're joining together the 2 carbons, and that's not going to work because methane means there's only 1 carbon, and that gives our answer of C for that one. So just following what it tells you, try and figure out what's happening here. In this question, we're dealing with lithium aluminium hydride. That is a reducing agent, and Tollens reagent we need to know is an oxidizing agent. We would react our lithium aluminium hydride with aldehydes and ketones, and that would react them back to alcohols. An oxidizing agent, on the other hand, would take alcohols and turn them into aldehydes and ketones. An aldehyde could be further oxidized into a carboxylic acid. One thing that can help us in questions like this is to sketch out each of the chemicals. From the sketches of the first two, the first one has to be a ketone because of the position of the C double bond O. And now there's a C double bond O because if you look here, this carbon has no hydrogens attached to it. Get a carbon on either side. Only way that works is if it's got a double bond with an oxygen in the middle. And for B, we'll have an aldehyde. Again, looking at what we've got here, we've got a carbon with only one hydrogen on it. There's a carbon to the left of it, which means it has to be double bond O, then the hydrogen off of the end. C, we've got to have an ether. Based on how many hydrogens were in the carbon surrounding the oxygen, this means this is the only way that's going to work. We have an alcohol because of the hydroxyl group for the last one. Ketones would be reduced by lithium aluminum hydride into secondary alcohols. They would not be oxidized by Tollens reagent, which means that is our correct answer. Aldehydes would react with both the lithium aluminum hydride and the Tollens reagent. Ethers would not react, and then the alcohol would not react with them either. That makes our correct answer A for that one. Next one, we talked about empirical formulas. We've got the simplest ratio. What this means is that you could have C2H6O2, C3H9O3, and both of these chemicals would have the same empirical formula. This means that we don't know if they would be isomers of each other. Isomers would have the same molecular formula, a little bit different. If we don't know which formula we have, they would have different masses. As I said, you could have the C2 or the C3 versions. Same functional groups. We don't know how the oxygens are arranged in the chemical. Not got enough information from just an empirical formula, but it is to do with the percentage by mass of each element. That's all we'd be able to tell just purely from an empirical formula. You get other information that can help you make better decisions on the exact chemical you've got. This question, we've got an lovely equation that we are trying to work our way through. We are asked here to work out the wavelength. So we are just wanting to use this pretty much as is. I'm going to write down that 1 over for lambda, which is the wavelength, equals, well, R is the 1.1 times 10 to the power of 7. In the bracket off then, we've got 1 over N1 is the energy level to which the electron falls. Reading this here, we're falling from the 9th to the 2nd. That's the one that I care about because it's the one it falls to. We're going to have 2 squared, like the equation says. That's minus 1 over the value from which it falls. So from the 9th, that's from in there. Going to be 1 over 9 squared. Close the brackets. We can then start to work our way through these values. 1.1 times 10 to the power of 7. In the brackets, we've got a quarter. Take away 1 over 81. This will give us that 1 over the wavelength will equal 2614198. We're asked for lambda, not 1 over lambda. We'll rearrange this to give us 1 over that answer that we've got. Will give us our final answer of... Now, in my calculator, this will kick out 383 times 10 to the minus 9. The values, the numbers, all match up with B if we just moved along to our decimal point, and that will change our power that we've got, and that will give us the 383, or 3.83 I should say, times 10 to the minus 7. Get from there. Next one, we have got another NMR question, we're told that we have got only one environment in this one. If we look at propane, we have different environments because we've got our CH3s, which are beside the CH2s, but we also then have a CH2, which is sandwiched in between the CH3s. That would not give you only one environment. There's more than one environment in that one. Propanol, we've got our hydrogen that's part of the aldehyde group, where we've got the H joined to the C double bond O. We've also got the CH2, which is beside the C double bond O and the CH3. Then you have the CH3 beside the CH2. Again, more than one environment for that one. Propanone, all we've got is two CH3 groups. They are both beside a C double bond O. This would make them have the same environment and the same shift in the spectra, which means that C would be a correct answer. Here, we've got our hydroxyl group hydrogen. We've got the CH2, which is connected to the OH group. We've also got the CH2 and then the CH3. Again, more than one, which means that is not going to be our answer for this question. Moving on here, we're asked for the greatest number of negatively charged ions. First, I would change my volumes and concentrations into number of moles. I'm going to use N equals C times V. Next, we need to focus on the negatively charged ions, as the question says. For the first one, it's going to be the nitrate, then our sulfate, then our chloride, then our iodide. For the first one, in every 1 mole of zinc nitrate, there are 2 nitrate ions. The little 2 in with the brackets is telling us. That means we're going to have to times the number of moles of the whole compound by 2 to give us 0.08 moles of nitrate. Second one just stays as is because there's only one SO4 within compound. Next, we have 2 chloride ions within our barium chloride, so that needs to get times by 2, giving us 0.06. The last one was just 1 iodide in the potassium iodide, meaning we believe that the same. So taking that into account gives us our correct answer of A. If you didn't do that, you would come out with B, which is incorrect. In this question, we're told the energy required to break one bond. Couple of options for how we do this. We're going to need to involve Avogadro's constant, which is to do with how many atoms or molecules there are in 1 mole of a substance. You can find that in the data booklet. So if one bond would take 3.22 times 10 minus 22 kilojoules, well then 6.02 times 10 to 23 bonds will require us to multiply those two numbers together. So 6.02 times 10 to 23 times 3.22 times 10 to minus 22. Pop that into our calculator. That gives us 193. Guess it'd be 844. The one that matches closest to that would be the bromine, which has been rounded to 194. And bromine, therefore, is our correct answer. That brings a close to the multiple choice. In this question, we're asked about how coloured light is produced when fireworks are ignited. This is to do with electrons relaxing, dropping down to a lower energy level and releasing energy. Depending on the energy gap, this will produce different colours of light. In this question, we're told that a firework produces light with an energy of 193 kilojoules per mole. We're asked to work out the wavelength of this light. This one we're going to use E equals LHC over lambda. You can find that in our data booklet on page number 4. It's here. L is our Avogadro's constant, H is Planck's constant, C is the speed of light, and lambda is the wavelength of the light we're dealing with. If we forget our constants, we can find them on page number 20, and we're dealing with all 3 of these here. What we can do is we can rearrange this so we can work out our wavelength. Our wavelength is going to equal LHC over our energy. Start to plug in our numbers. We're going to have Avogadro's constant of 6.02 times 10 to the 23. We're going to have our 6.63 times 10 minus 34. We're going to have our 3 times 10 to the power of 8. Again, taking those values from here in the data booklet. What we need to watch out for is our Planck's constant is in joules per second versus what we are told is our energy in kilojoules. We need to make that conversion. I would probably just change the energy, times that by 1,000 to make it joules, which will be 193,000. We can then plug that into our calculator. This will give us our wavelength in meters. That gives us 620 times 10 to the minus 9 meters. Nanometers is 10 to the power of minus 9. This means that we are going to have 620 nanometers, like the question wants from us. That gives us our answer there. We're asked to identify the metal most likely to produce this coloured light. 620 nanometers. We can go to the data booklet. We're looking for flame colours, which we'll find on page 16. We have 620. Calcium matches 620, giving us our answer there. In this question, we're asked about the laws of thermodynamics. Our first law of thermodynamics is that energy cannot be created or destroyed. For the second law, the total entropy of the reaction and its surroundings will always increase. If we're asked about the third law of thermodynamics, this states that the entropy of a perfect crystal at 0 degrees Kelvin is going to be 0. Moving on, this question, we're asked about the temperature at which a reaction will become feasible. This will rely on delta G equals delta H minus T delta S. The reaction will become feasible when delta G equals 0. This means that 0 will equal delta H minus T delta S. Rearranging gives us that T delta S will equal delta H. Therefore, T equal delta H over delta S. Looking at our values, we've got 1 in kilojoules and we've got 1 in joules. We need to change them so they're both the same. I'm going to again go for turning the first one into joules. So 250,000. Popping them in. That gives us 250,000 divided by 509. Popping that into our calculator, get an answer of 490, and that is in Kelvin. That gives us an answer of 491 Kelvin. In this question, we're asked about the shape of a transition metal complex. We are asked about our hexa aqua nickel 2, which looks like this. Here, we've got one thing in the middle, 6 things around it. The shape that involves that arrangement is going to be an octahedral shape. We've got 6 bonding pairs of electrons around our central ion. Next one, we're asked about the coordination number of the nickel in the intermediate. We're looking at how many bonds it's making. When we go up to look at our intermediate, we've got 1, 2, 3, 4, 5, 6, 7 bonds around the central nickel, making our answer 7 bonds. Coordination number is 7. Next one, we're asked about complex X. Let me bring this down just to make it easier to keep track of. First thing I'll deal with are our 5 water ligands, and that's going to be penta aqua. Next thing, we have an amine, and with these groups in the transition metals, it's double MIN. That alphabetically comes before aqua. Doesn't matter about how many of them there are. We need to put that at the beginning. Now, we could say it's mono amine, but less writing, I'm just going to go for amine. Penta aqua because there's 5 waters. Next, we need to look at the middle ion, the transition metal. We have nickel. Because we have a positive ion, we just write nickel as is. If it was a negative ion overall, we would have to change the name of it. So it's just going to be nickel. Like so. Next thing is all of the ligands involved, so the water and the amine, they are both neutral ligands. There's no charges on them. This means that the 2 plus overall charge has to come from the nickel, which means our nickel needs to have a 2, so Roman numerals 2 as our answer. So amine, penta, aqua, nickel, 2. There. Monodente, dente comes from teeth. And mono meaning 1. This has when we have a 1-toothed ligand, it makes 1 bond to the metal. So forms 1 bond. The other option you could talk about it donating 1 pair of electrons to the metal, forming that 1 bond as well. In this question, we're asked to determine the overall order of this reaction. We need to look at the rates. We need to look at the orders of each reactant and then add them together. We have no numbers above either of them. This means that it has to be first order with respect to the nickel complex, and it also has to be first order with respect to the amine. This means that we're going to have an overall order of 2. We have second order reaction here. Next one, we have to calculate the value for the rate constant, including the appropriate units. So we'll deal with the numbers first of all. So we can start to put in our values that we are given. The rate is 1.3. So 1.3 times 10 to the power of 2 equals, okay, we do not know. It's going to be that times 0.1 times 0.25. Moving this along, we then have 1.3 times 10 per 2 equals k times 0.025. Rearrange it for k. K equals 1.3 times 10 power of 2 over 0.025. Pop that in your calculator. That gives us 5,200. 2 ways to approach the rate constant units. You can either just memorize all the different versions that you get, or we can work them out. I'm going to go for the working it out way. So our K, what we did is we had our rate, and our rate is in moles per litre per second. I'm going to write that in. So MOL L to minus 1, S to minus 1, divided by both of the concentrations were in moles per litre. So we have MOL L to minus 1. That is squared. What this means we can do is we can cancel out one of the moles per litre. This leaves us with S to minus 1 divided by moles per litre. We want everything up on the top line. We don't like to leave it as a fraction. So our MOL will become MOL to minus 1. The L to minus 1, we move it to top, which is going to be L. And the S to minus 1 would stay the same. We tend to do it by alphabetical order. It does accept all the different versions because we have a positive power. Then we'd have our MOL to the minus 1. Then our S minus 1 to do that. That last one would be how I'd probably prefer to leave it. Next one, we're asked about different types of hybridization. In this case, we have got a benzene ring. When we're dealing with single bonds between the carbons, this would be our sp3. If we had triple bonds, that's going to be our sp. And then for double bonds and our benzene ring, we're going to end up with sp2 hybridization. Next one, we're talking about the differences between pi and sigma bonds. A sigma bond is an end on overlap versus our pi bond, which is a side on overlap of orbitals. That next one, we're asked about how conjugated systems affect the wavelength of light that's been absorbed. We have, in this case, got a very small, short conjugated system. So the short conjugated system results in large energy gap, and that's between the highest occupied molecular orbital and the lowest unoccupied molecular orbital, so HOMO and LUMO. And that corresponds to UV light, not visible light. This question, we're dealing with a synthesis reaction. We have a benzene ring, which is adding on a propane. Here, what we're having happening is the benzene ring is being attacked and being substituted into. This has got lots of electrons. This means it's going to be undergoing electrophilic substitution. We had hydrogen, benzene ring, we have C6H6. And instead of having hydrogen at the end, we have replaced that with a different group of atoms. And that's where the substitution part comes in. So it's electrophilic because there's lots of electrons in the ring. And it's substitution because we're swapping out hydrogen for other atoms. Next question, we're asked about the molecular formula. So that's the number of C's and H's that we've got in each of them. A couple of things to bear in mind. First thing is that at each of these points here, there's going to be carbons. So we have our 6 carbons in a ring, 7th there, 8th there, and then 9, C9. In terms of your H's, off of the benzene ring, each of them will have a hydrogen. So we've got 1, 2, 3, 4, 5. Don't have any hydrogens here. This point here, this carbon, we're making 3 bonds currently, which means it needs to have a hydrogen there. On the end here, these will be CH3s. Means we need to have 3 hydrogens on there and 3 hydrogens on here. Getting them up, we've got our 5 from the ring, 6, 7, 8, 9, 10, 11, 12. So C, 9, H, 12 is our answer for that one. In this one here, we need to think about stability. And it's stability of a carbocation. It's a positively charged carbon that's involved in this one. Here we've got this on at the end, which makes this a primary carbocation. And in this one here, we have a secondary carbocation. So because it's attached to carbons, that will help stabilize the carbocation. The arrangement takes place is a more stable carbocation is favoured. Next up, we're dealing with calcium carbonate and undergoing a back titration. Back titrations are really important when you have a reactant that is insoluble in water. Calcium carbonate, component of chalk, calcium carbonate, insoluble in water. Now we come on to a calculation involving our back titration. We're asked first to calculate the number of moles of hydrochloric acid that reacted with the calcium carbonate in the limestone. First thing we need to do is we need to decide which values we use as our titer values. We want concordant results within 0.1 in this case of each other. That is going to be for our sodium hydroxide. I'm going to start over here. We have sodium hydroxide. Average would be 10.15. We have 0.3 mole per litre sodium hydroxide. So we're going to do N equals CV. N equals 0.3 times 10.15 times 10 to minus 3. We want them in litres. It gives us 0.003045. Next up, we need to do our ratio. We need to compare the two chemicals. Got our sodium hydroxide and our HCl. We're using this ratio in here, which means that we've got a 1:1 ratio. This means that we would have 0.003045 moles of hydrochloric acid left reacting for that. Now, this is the stuff that's remaining. So there are 0.003045. This is remaining. With these questions, we need to look at the scaling factors in it. This was for a 25 centimetre cubed sample. If we go up, this came from an 100 centimetre cubed flask. This means that in 100 centimetres cubed, we're going to end up with 0.01218 moles. We added 25 centimetres cubed of 1.5 mole per litre hydrochloric acid. So I'm going to now work out our value at the start. Again, we're going to use N equals CV. 1.5 times 25 centimetres cubed divided by 1000 gives you 0.025. Therefore, our number of moles, it gives us 0.0375 moles added. Work out our moles reacted. We're going to do our start minus the remaining, the stuff at the end. That's going to be 0.0375 take away 0.01218. That gives us an answer of 0.0253 moles. Moving on, we are told a statement that we're looking for a calcium carbonate content greater than 95%. We're trying to see, would this be able to produce that amount of the chemical? We know that there was 0.0253 moles HCl reacted. We go up and look at our other equation for the ratio now. It's a 2-to-1 ratio between hydrochloric acid and calcium carbonate. So we're going to apply that now. HCl, CaC3. It's a 2-to-1, means it will be 0.0253. Divide that by 2 gives us 0.01266 moles. Next, we're going to turn that into a mass of calcium carbonate. Table look, it tells us that N equals M over GFM. So our mass equals N times GFM. It's going to be 0.01266 calcium carbonate. We can work out a GFM. We'll just check if it tells us up here. It does not. Let's go through it then. Got 1 calcium, 1 carbon, 3 oxygens, 1 and then 3. Got 40.1 for calcium. We've got 12 and we've got 16. That will give us 100.1. That gives us our mass of 1.267. That would be in grams. We have to work out the percentage of the chemical that is calcium carbonate. So our percentage is going to equal the mass of calcium carbonate, which is 1.267 grams. The total mass of the limestone was 1.3. And then we want to make that into a percentage. When we pop that into our calculator, it gives us 97. I'll round it to 97.5%. And that would be yes. For this question, we'll first deal with the possible sources of error in this analysis. First thing we'll deal with is the possible source of error. First thing would be whether or not the solutions had been standardized. This could be done using a primary standard. We could then talk about the characteristics that primary standards must have. Those being high purity, stable in air and solution, readily soluble in water, and a high formula mass. Linking it back to the question, we had sodium hydroxide and hydrochloric acid are not primary standards. We could then talk about the chemicals we could use to standardize them. Salicylic acid and sodium carbonate would both be used to standardize your sodium hydroxide and your hydrochloric acid respectively. The accuracy of the equipment would make a difference as well. But A grade glassware has a lower error than B grade glassware. Those errors are usually given as a plus or minus a certain value. Incorrect reading of values from a scale could impact your results that you get. They should always be taken from the bottom of the meniscus, the little bubbly part. When measuring masses, there could be some of the reactant or products being lost, and we should do it by weighing or measuring the mass by difference. In this case, you would measure the container empty, measure it with the sample, and then remeasure it at the end to make sure that all of the chemical has been transferred, or you can readjust how much of the chemical you actually did add. Your choice of indicator will matter depending if you're using strong or weak acids and bases. Got hydrochloric acid and sodium hydroxide. So we have a strong acid and a strong base. We want an indicator that will change colour around about pH 7. We could then bring in the data booklet and we can look at the different indicator values that they give us. And here, so we're looking for one that changes colour around about 7. Something like this one. Or this one. It would probably be quite good ones to go. So them. We have bromo. So bromothymol blue. Or the other one, phenol red, for example. We could then talk about a control being ran. This would use a known concentration of our solution. Because we're determining our percentage of calcium carbonate, if we made up a calcium carbonate solution of a particular concentration, we should be able to get results that then lead out in our calculations to giving us the correct value, or it will at least flag up how far out we are. So if we're going to end up with a higher or lower result, depending on how well we have planned our experiment. There are probably more things that we could talk about. Get all 3 marks, you need to be good. You get 2 marks, you need to be reasonable, and 1, you need to give a limited answer. Moving on to our next question. Here we're asked for an electron configuration for cobalt ion in this particular configuration. First of all, we need to check how many electrons does cobalt have, just originally. Cobalt has 27 electrons. So the first thing I would do, I would probably just figure out the full arrangement first of all. Go back to what we've done quite a few times now. We've done 1s, 2s, 2p6. That brings us to 10. We then have our 3s, 2, 3p6. Now up to 18. We'd next go to our 4s, as that would fill first. Gives you 20. And then we have 7 left, and those 7 will have to go in the 3d orbital. If this was in ground state, this would be our answer. However, we have joined it on to 2 chlorines. Chlorine would lose 1 electron. It would be Cl negative. We've got 2 of them, meaning we've got a total negative charge of 2 negative. Our cobalt then has to be 2 plus, and that way the charges will balance out. We have 2 of our Cl minuses. With transition metals, we are going to lose the 4s electrons before the 3d7, because when they're occupied, that changes the energies associated with them. Our correct answer then would end up being 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d7 to finish it off. Next one, we have to determine the oxidation number of the cobalt in this particular chemical. We have got to have a 2 positive charge. As I said before, because of the 2 chlorines, each would bring a value of 1 negative. Therefore, our oxidation state would be +2. You can write it as 2 positive. That tends to be more considered the charge of it. So both of them would work out correctly. Next one, we're asked to talk about a gravimetric determination. In this one, what we want to do is we want to take our sample and we want to convert it into a stable product, which we can then analyse to see how much of each of them we've got. What I'm noticing is that we've got to get rid of the water, because it's in a number of waters. We want to turn it just into cobalt chloride. First thing we're going to do is need to heat the substance. And we would describe our technique to be heating to a constant mass. Okay, how do you do that? First thing you need to do is you need to heat the substance. Then you want to cool it in a desiccator to prevent the absorption of water. Next, you want to measure the mass. And then you're going to repeat heating and cooling until you get to a constant mass. That way we've driven off all of the water and we've left with just our cobalt chloride, and then we can look at the masses that were lost and then try and figure it out, which I'm presuming is what we're going to do here, which indeed it is. So what can we learn from what we've been told? Well, we can look at the mass loss between our starting value and our end value. And the mass lost has to be water, because that's what's been driven off. Other questions will have different things that are given off, but in this one, we've lost our water. That's got to be that lost mass. I'm going to do 0.372, take away 0.204. Going to give me an answer of 0.1, and that will be 8 grams. Next up, I'm going to change them both to number of moles. That will make our life a lot easier. So first thing I want to do is work out my moles of water, like that. As we've done before, N equals M over GFM. N equals, it will be that, 0.168. Divided by, oxygen has a mass of 1. 2 hydrogens would be 2. That gives you 18. That should be one that you're fairly familiar with from the number of times you've done it. It gives us 0.00933 moles. Next, I want the moles of our cobalt chloride. That is COCl2. I know off the top of my head, 35.5 for our chlorine. Cobalt, I'm not so sure of. Let's look it up. And here, 58.9. Next up, 0.9. Two of them will be 71 plus the 58.9. That gives us 129.9. Then carry out N equals M over GFM as we've done for water. It's going to be 0.204. That over 129.9. That gives us an answer of 0.20, and it goes 157 moles. Here, easiest way of doing it is to then just divide by the smallest value. So for each of them, divide by 0.0157. Dealing with the cobalt chloride first, that's going to be just 1 because it's 0.00157 divided by itself, 0.57. That's just going to give you 1 mole of that. Checking out the water, we have actually got 0.00933 divided by 0.00157. We're wanting to get this to a whole number, so we can tell them the value of N. Calculator spits it out as 5.94, round that up to 6, and that means our value of N equals 6. So there's 6 waters for every 1 cobalt chloride. Value of N equals 6. Something like that, just to make sure they're aware where we're going. Try to lay it out so it flows from left to right to make it fairly obvious, hopefully, of the kind of process we've gone through to get to our value of 6. Next up, we're talking about a complexometric determination of, in this case, cobalt. A complexometric reagent that we need to be aware of is something called EDTA. The idea is it will bind on to our cobalt, and using a particular indicator, something like a mur oxide indicator, changes colour when they are joined or not joined. Ethylene diamine tetraacetic acid is its full name, more commonly and more easily known as EDTA. Next one, we're asked to suggest another technique that could be used to determine the concentration. With transition metals, it tends to be coloured compounds. This would mean that something like a colorimeter would be quite a good way of determining what's going on with this. So my answer then, I'd go for colorimetry, where you test the absorbance in the particular wavelengths depending on what colour it is. For that, other ones include, I suppose you could, because it's the metal involved, you could do emission or absorption spectroscopy, and that way you would know what colours of light have been absorbed or given off. So heat it up and measure the light that's been emitted, or shine light into it and see what's been taken in, what's been absorbed. Okay, something like that. Again, possibly some others one, but I would stick to colorimetry as a good alternative to that. Next one, we're asked to look at an empirical formula, and we're told it's got carbon, hydrogen, and oxygen. We're asked to try and prove this. So that's quite good, because if we start doing calculations and they don't give us the empirical formula CH2O, means we've done something wrong. The first thing I would then do is think of, well, this does not add up to 100%. This means there has to be, the remaining percentage has to be oxygen. So our oxygen can equal 100, take away, that would be 46.7 together. That gives us 53.3%. If we imagine that we're dealing with 100 grams of the substance, this means that we can just change or take our percentages as being masses, and it will make our life hopefully a little bit easier as we move forward. So I'm going to say that we've got 40 grams of carbon. If we compare the number of moles, this again will make our life easier to compare between. So to do that, I'm going to divide it by the mass of a carbon, which would be 12. And this will give me an answer of 3.33. Next up, I'm going to do the same for hydrogen. I'm following this pattern because that's how they want it in the answer. Again, it wouldn't matter too much. It just will make hopefully my life easier keeping track of everything. We have got 6.7 of that divided by how hydrogen is 1. And that just gives us 6.7. For this one, we're just looking for the mass of one atom of it. We're not worrying about the GFMs. We're just looking for the mass of a hydrogen. When we get to our oxygen, we're dividing by 16 then. Of oxygen gives you 53.3 divided by 16 gives me 3.33 as well. If we look at them, you can look at the ratio. We've got the same value, rounded a little bit, but we've got the same value of carbon and oxygen. That makes sense then, that that's 1 to 1. And then our middle value is slightly double the value of the oxygens. The way, if it didn't work out quite as nicely that we can see that's what's happening, you would do what we did previously by dividing by the smallest number. So 3.33 divided by 3.33 equals 1. 6.7 over 3.33. Just a little bit above 2, but we're dealing with an empirical formula, so we want that as 2. And then 3.33 over 3.33 again gives you 1. A 1 to 2 to 1 ratio, CH2O, just like that. Moving on, we are told a simplified mass spec of our compound. We need to keep in mind that it is CH2O 2, and then O. An empirical formula shows us the simplest possible format. This means that we could have C2H4O2, we could have C3H6O3, and so on and so forth. To figure this out, I'm going to go to this peak here, which is the molecular ion. It's the largest value that we've got, and that gives us a value of 90. If I go through each of my options, bear in mind it always has to be some multiple of C2H. Carbon is 12. Hydrogen, sorry, is 1. And we've got 2 of them. I've added up. So 2 times 1 and 1 times 16. That's going to give us 12, 13, 14. And that's going to give you 30 as our answer. That's not going to work. You would double it up to get to the next one. So if the first one has a value of 30, C2 would have 60. So this means it has to be C3H6O3 because that's the one that follows the pattern. Next up, we're asked to suggest a possible fragment that would be responsible for the peak at 45. So here what I'm looking for is a combination of carbons, hydrogens, and oxygens that make a mass of 45. If we had carbon chain, that would be 15 from the first one, plus CH2 in the middle would give you 14. That takes you to 29, leaving 16, so that would be an oxygen. We could have an oxygen here. This would then need to have a charge on it, because it's an ion, not a atom or a molecule. So I'm going to put positive charge there. Next thing we could have COOH. So this would make it part of the carboxylic acid family. And then that would need, again, a little charge involved there. You have to have charges involved in your ions and your fragments that you're going to put. Which one will I pick? Let's go for COO. Let's just go H, and typically, actually maybe write it the other way. COOH, and then you can have your positive charge out there. But the main thing, number one worry is, does it add up to 45? Yes, and then you need to think about where the positive charge would go. So this COOH would work nicely for this one. In this one, we're asked about something of rotating plane easy for me to say, polarized light. Here, this means that we've got to have a chiral molecule. And for chiral things, this means that there has to be 4 different groups on a carbon. So we know we've got 3 carbons to deal with, so I'm going to put them all in a row. And then we need to try and figure out how we can arrange this so we've got different things joined on different carbons. We need 4 things attached to the carbon. Because we need 3 oxygens, it's likely, and because of one of the options I had above, it's likely to be a carboxylic acid. Now this one's not going to be a chiral center. You have a double bond to an oxygen, which means it cannot make 4 bonds to different groups. So that's not going to work. I'm thinking that this one in the middle, though, might be a good idea. I've still got hydrogens and 1 more oxygen to play with. So if I was to put on an OH here, something like that, H down there, and I've got my H's along here. When it comes to dealing with if you've got 4 different groups attached, it's not just what does it bond to. So if I look to the left and right of the one I'm claiming, so I'm claiming this middle one is chiral. You look at both sides of it, well, they've got the same thing, it's attached to carbon. True, however, you need to look at the whole of what it's joined to on the left and the right. So what I'm trying to get at is here, you've got a CH3. On the far side, you've got C double bond OOH. Above it, you've got C, just an OH group, a hydroxyl group. Underneath it, you've got a hydrogen. Those are 4 different groups attached to that carbon in the middle. So our central carbon is going to be our chiral center. Main thing is that you join them up correctly, so bonded to the oxygen, to carbon, carbon to carbon, etc. You have to make sure that everything's making the correct number of bonds. Hydrogen makes 1, carbon 4, and oxygen 2. And then you also have to make sure you've got one carbon that's attached to 4 different parts. Like so, moving on to the next one. We're asked to draw a formula for P. We should recognize that this is a substitution. Other thing we may recognize is that the C2H5O negative is an alkoxide. And when you take a haloalkane, we're going to get rid of this Cl and we're going to form a chemical called an ether. When I'm drawing this out, first thing I'm going to do is copy my left-hand molecule where we've got our carbon with the 3 H's. That's this part here. Then goes to carbon with a methyl group. A hydrogen coming down. We then get to the carbon, H and the H. So I'm now here. Next, I'm going to then join that to the oxygen. Then got 2 more carbons coming off of there. I put in my chemicals here. And that makes our correctly drawn structure. For part B, we're asked about chemical Q and what type of chemical we are making. We need to be recognizing C triple bond N as a nitrile. Nitriles are this is being hydrolyzed. What type of chemical are we making? And that is just a carboxylic acid. Next one, we've got a mechanism for forming the nitrile in reaction 1. So we're starting off from our haloalkane. So I'll just draw it out first of all. Okay, we've then got our nitrile, where we've got our negative charge on here. It's going to be driven by the fact that the chlorine is more electronegative. That makes that slightly negative, and this carbon is slightly positive. This makes this susceptible to an attack from an nucleophile, like our nitrile group. When it comes to our mechanisms, we're going to be forming new bonds, which means we want to have our double-headed arrow. I'm going to want an arrow coming from here, attacking into there. This is then going to cause change over here, where we're going to have our electrons going towards our chlorine. This is going to be most likely going to happen as an SN2 reaction. With our nitrile, we're going to then form our transition state. Essentially looking the same, except from we've got extra bond now to our NC triple bond. With our intermediate, we'd want to put our square brackets around it. We're going to have our negative charge. And then what would happen is, moving forward, the chlorine would then be removed, and then that would form your nitrile product that we're looking for. So we need to make sure our curly arrows go from the negative charge of the nucleophile to the carbon that's attached to the chlorine. Then another bond from the C to Cl bond out to the chlorine would work out with this one. Asked which solvent we should use for reaction 2. Reaction 2, what's happening here? We're forming a carbon-to-carbon double bond. This is an elimination reaction. The solvent is good at helping to carry out elimination reactions is going to be ethanol, so an alcohol. So elimination ethanol is what I was told, and that's what stuck in my head. So ethanol would work out quite nicely for that one. Here we're asked to use a percentage yield to work out how much of the product we would produce. If you don't remember what that equation is, it is in the data booklet. We're going to be using this relationship here. I'm just going to plop that down at the bottom. So we have a reactant in 1-chloromethylpropane. We also have our product. We're asked about the methylpropane. So we're going to take our 1-chloromethylpropane. I'm going to do N equals M over GFM. That's going to be 1.85 over. So we have our chemical we are dealing with. We can work out the GFM. There are 4 carbons. There are 3, 4, 5, 6, 7, 8, 9 H's and 1 Cl. Carbon, as always, is 12. We've got 4 times 12. We've got 9 times 1 for the hydrogens. And we've got 1 times 35.5. Adding them together gives us 92.5. And working out our number of moles, which is 0.02. Next, we need to think about our ratio between our two chemicals. But in this one, we're going to have a 1-to-1 ratio because we're making the carbon-to-carbon double bond by eliminating hydrogen and chlorine. So 1-to-1 ratio, this means that we will also make 0.02 moles of methylpropene. We're told the molar volume is 23 for methylpropene. This means that 1 mole would give us 23 litres. We've only got 0.02 moles of it. This means that if we times both sides by 0.02, get to our answer. So our number of moles would, our volume would be 0.46 litres. Going down to our percentage yield, but we know that we're only 60.4% efficient. We can do this in one of two ways. One way is to put it into our equation. So we've got 60.4 as our yield equals actual is what we're trying to figure out, divided by 0.46, which is what we should, or we maximum we can make, times 100. Rearranging it, we get 60.4 over 100 goes actual over 0.46. Then you get 60.4 over 100 times 0.46. That will give us our actual yield. The other way, which gets you straight to that bottom line, is just take 60.4% of the 0.46 that we could make, and that will also get your answer. That's where it comes from. You can rearrange it however you like. Just type in to your calculator 64% of 0.46 gives us an answer of 0.27. Give myself a little bit more room. Type it into your calculator, you get your actual equals 0.278 litres. If you wanted it in centimetres cubed, 278 centimetres cubed. Times it by 1,000 to go from litres to centimetres cubed. In this one, we're asked about our conjugate base. Our acid is going to lose H plus or H3O plus. That's then going to form our conjugate base. So when it reacts or when it gives up its H pluses, it's going to become our conjugate base. We're starting off with our ethanoic acid, which would be CH3Q. That's then going to dissociate into CH3, COO negative plus our H plus. So we have our acid, we have our conjugate base. That means that our conjugate base is CH3COO negative, or the ethanoate. In the data booklet, you will find these equations. Here we've got another water involved, which just means that we, instead of having H plus, we have our hydronium, which is the H3O positive. In this one, we're just focusing in on the part that's left over acid after the acid dissociates. This one, we're asked about a buffer solution. Again, data booklet will tell us how to do it. On this page, there are lots of different pH relationships. The one we want for a buffer is where we have an acid and the salt of that acid involved, which means we're going to use pH equals pKa minus log to base 10 of acid over the concentration of acid over concentration of salt. Pop that into here. The first thing I'm going to need is the pKa of ethanoic acid. Back to page 14 we go, and our pKa we're going to use 4.76. So let's pop that in. We have pH equals 4.76 minus log to the base 10 of, now I need the concentration of the acid. We are told that will be 0.5 over. To work out the concentration, I'm going to do the number of moles first of all. It's going to be N equals M over GFM. N equals 4.1 over 82. That will give us 0.05 moles. That is in 250 centimeters cubed. of the solution. So then to work out our concentration equals number of moles over volume, 0.05 over 0.25. That gives us an answer of 0.2. I'm going to put 0.2 on the bottom, up a little bit. And at this point, you just pop that into our calculator, and then spitting that all through, it gives you 4.36 as your pH value. Things to watch out for: number one, make sure you're looking at the correct volumes when you're trying to work out the concentrations. Make sure you're using concentrations to put into it, and make sure you do the acid on top and the salt on the bottom, and that will hopefully give you the correct answer. Moving on to the next one, we're talking about buffer solutions. And we're asked, why will the pH of this buffer solution remain approximately constant when small volume of water is added? Okay, so what's going to happen when you add water? Well, you're going to dilute the concentrations. You're going to dilute the concentrations. And you're going to dilute the concentration of the acid and of the salt. So because both of them are going to be diluted in the same way, the ratio of acid, salt, which is what this bit is representing, that's going to stay the same because both of them will lower, and then that will keep that value the same. I'll show you an example in a wee second. Is changed. So for our values, we had 0.5 over 0.2. Now, if we were to dilute them, they diluted them by 10, that means we're going to have 0.05 over 0.02. And both of those values will be exactly the same. 0.5 over 0.2 gives us 2.5, and 0.05 over 0.02 would also give you 2.5. That's what my rambling was trying to say, that because they're both moving down, then we get a ratio that stays the same. Next one, we have got asking about buffer capacity. So how well a buffer resists pH changes. Okay, so we're asked to prepare two different buffer solutions. We'll try to see which one has the larger capacity. Right, first thing is you need to be doing a fair test. So we want equal volumes of both of them. So take equal samples of the two buffers. Then if you add the same volume of, again, you want the same concentration of the alkali that we're adding. Same volume, same concentration of alkali, and measure the pH that's going to rise. So it's going to be rise, measure the pH rise. The smaller, so the smallest pH rise is the, or has the larger buffer capacity, has the larger buffer capacity. Just see what it is. So the one that takes more volume of the alkali to raise the pH value will be your larger capacity one. Next one, we're talking about drug. So we have drugs and medicines in this topic. It's anything that alters biochemical processes in the body. No other way of learning it than just learn it. It's just a straight up learn the question. If the definitions of a medicine, we want to be talking about the beneficial effects. It has a beneficial effect on the body rather than just altering the biochemical processes. Now, I have seen this question before, so one of the simplest way of separating the different types of drugs would be into our agonists and antagonists. So with that being said, we've got something that's blocking. So if you only focus on that word, you would have your antagonist would be the answer you'd put, because that blocks the pathways, whereas an agonist mimics that. The thing you need to watch out for with this one, it's leaning more towards biological question when we're talking about enzymes. More binding to the active site of an enzyme. That means that this question is therefore going to be to do with inhibitors and blocking the active site. So this is one of those questions on first sitting I would have more than likely got wrong, because I was just so used to it just being either agonist or antagonist. But in this question, inhibitor, because it's enzymes involved for that one. That's something to maybe watch out for. They've just used that type of drug rather than the usual type of ones. Next one, we've got a little calculation one. These ones, I'm going to take the first thing it tells me, which is 0.68 milligrams in 1 kilogram of body weight. That's in 1 kg. So we're dealing with 8.4 kilograms. Go between 1 and 8.4. I'm going to times by 8.4. Do the same on the other side. So we're going to have 0.68 times 8.4. That gives us 5.712 milligrams. For that, now what are we talking about here? Right, so we've got our milligrams. We're looking to work out dose we've got. So we are looking for concentration. Okay, so ppm, also known as milligrams per kilograms. Now this one's a bit different because we've got volume, so that would then need to be still milligrams, but per litre kilograms. Like that would make sense. Let's try that. If I change this into litres, I want to divide by 1,000. I want to get 0.023 litres. So then if I do our new value, like it was 5.712, that's the mass divided by our volume. And that will tell us how much our concentration is. Let's try this. 5.712 over 0.00231. That would give us 2,473. That's going to be your P, which is, I've just checked, is the correct answer. It would round it, you could round it up, because they gave you it to 2 significant figures, so we could have rounded to 2 significant figures in our final answer. Another way that maybe might, well, it works as well, if we said that we've got 5.712 milligrams in 0.00231 litres, and we are talking about per litre, is the way that the ppms work, either p per litre if it's volumes or per kilogram if it's in masses. So we want to get that down to 1 litre. So you divide any number by itself, that will give you 1. So divide by 0.00231. I do the same on the other side, and that's what I've done here. So I have actually carried out that same process, just in a slightly different layout. But we are scaling, and that will give you your answer of the 2,473 milligrams in a litre, or 2,473 parts per million for that one. I am much more used to seeing it in milligrams per kilogram. That would again be my go-to one. It just seems like part B and part C, they have went out their way to pick ones that aren't quite the most common ones, which is well within their rights, and that's how you would end up with that one here. Next one, we are asked to discuss isomerism and the role it plays in chemical synthesis and drug action. First thing is there are different types of isomers. We have structural isomers. These are the ones that have the same molecular formula but different structural formula. These are the ones that you would have dealt with at National 5. That'd be something like cyclopropane and propene. Next, we have stereoisomers. These are ones that have the same molecular formula and the same structural formula. They arrange differently. They have a different 3D arrangement. Then give an example. These are the cis and trans ones. You need to have restriction of movement, which means a carbon-to-carbon double bond will help do that. So both of these chemicals, they are both 1,2-dichloroethane. Difference between them is where the chlorines are in three-dimensional space. Here we've got one on either side. Opposite sides means it's trans. 1,2-dichloro, whereas the other one, they're on the same side, which means it's cis. Still 1,2-dichloroethane. This one is opposite sides. Whereas in the other one, we have them on the same cis, same side. There must be restriction of rotation. And that happens when you have C double bond O or a ring. That will potentially lead to that. So these ones we just talked about, those are your geometric isomers we have there. Now, this can affect, the geometric isomers can have different melting points and boiling points. Next up, we get to optical isomers, and we're looking for a chiral center. That's when we've got 4 different groups or atoms attached to carbon in most cases that we're dealing with anyway. So we could show that with a little diagram. We can do, we've got the one thing there, carbon in the middle, then have our tetrahedral shape being shown, something like this. And that middle part would be your chiral center. And this allows, or this gives rise to non-superimposable mirror images. That's quite a good term to just get memorized. So if you were to reflect this in the mirror, the W would stay where it is. Carbon would be here. Our Z is heading, in our left-hand one, it's going from the middle down to the right. So in our one, we would end up with that coming down to the left, as you said there. The Y as well is going towards the mirror. Again, you still keep that, and then still have the orientation like so. The X is going down to the left, so we would then make that go down to the right. And depending on what parts, what atoms were there, you would just write them in if the question wanted you to draw them out properly. It's non-superimposable mirror images. The other thing would be physical properties would be the same. It's only how they deal with polarized light. So enantiomers is another word we can talk about, the 2 different versions of it. They have identical physical properties, except how they rotate polarized light, also described as being optically active. Moving on to talking about the drug action here. Optical isomerism is important in biological systems. In nature, you'll have one of the versions will be present, whereas in a lab, both versions will be made, or enantiomers, whatever you want to call it, isomers. Now, the active site of enzymes will only be able to work with one of them. And drug receptors may cause adverse effects with the wrong isomer. Famous one is the chemical that was used to treat morning sickness and nausea during pregnancy, called phthalimide, which did one enantiomer stopped the nausea, the other one caused deformities in the unborn baby. This is because both of the enantiomers, both of the versions were present within it. Okay, here we're using a relationship that they give us, PV equals nRT. They tell us what all the different things are. Let's see what we are told then. So first thing, we have a mass, which we are not dealing with yet. Next thing, boiled to produce a certain volume of gas. That is in centimeters cubed. That's going to be our V. So we are told that that would be then 0.259 litres for that. We are told our temperature. And we're told our pressure. Let's plot this in. We have 101 times 0.259 equals N, which I'm presuming is what we're working out, times R, it says here, is 8.31. Plug that in, times temperature, which is 353. Move that down here. Rearranging this, well, we want to get rid of a times by those two numbers. That will move across and become divide. So rearranging it, we get n equals 101 times 0.259 over 8.31 times 353. You could work them out individually, or I'm just going to make my calculator do all the work for me. So that tells us the number of moles that we have got within this question. Next thing then is, well, we're asked about the gram formula mass. That means we're involving n equals m over GFM. Therefore, we are wanting GFM, so GFM equal mass over number of moles. Told us previously that we had 0.518. That's going to be divided by the 0.00892. Popping that in gives me an answer of 58.1. That would be our final answer that we got in grams per mole. Next one, we suggest a liquid carbonyl compound used in this experiment. Okay, so we need to find something that has carbon double bond, which could be a ketone or aldehyde. The GFM has to be 58.1. Now, I think the one's not going to help us too much. Let's have a little look at what we can have then. So if we had just one carbon and double bond O, and then here we would have 12 from the carbon, 16 from the oxygen, and 2 from the hydrogens. Not going to work, too small. Bump it up a touch. So let's try 2 carbons. Carbons here. We have now got 24 from the carbon, 16 still from the oxygen, and 4. It gives you 44. Not quite, but we are getting there. So next thing to do is put on a third carbon. Something like that. You've got 36 from the carbons, 16 from the oxygen, and 6 from the hydrogens. 40, 52, 52 and 6 is 58.1. We'll just we'd get that one. The other way it could be drawn is we have the double bond O in the middle. We'd have C double bond O. We'd then have our carbon here with our H's on there. You have your ketone on the left, sorry, your aldehyde on the left. So the C double bond O is at the end. This would be your aldehyde. There's 3 carbons. So this would be propan al. Or you could have propan on with the carbon-to-carbon double bond middle. We're not told which version it is. They're not telling us about any reactions that happen or anything like that. So either of those would work. Propanal or propanone. Next one. Asked here to suggest why this would not be suitable to determine the gram formula mass when the liquid sample is butanoic acid. Gonna be something to do with the temperature. The thing I'm thinking is a water bath gets up to 100 degrees. That's the hottest a water bath can go. And if we check out the melting points and boiling points of butanoic acid needs to get raised to 164 degrees. This would mean that it's unable to get hot enough. So water bath unable to heat butanoic acid up to the required 181 degrees, 164, sorry, for the butanoic acid. Next up, we're asked for an equilibrium constant. Equilibrium constant, we are wanting to put our products, concentrations of the products over the concentrations of the reactants. Look at what we've got. We have got all solutions. So we're going to put our capital K equals concentration. What's only the I, the negative on that side, divided by our I2, I negative. Well, next up, we're asked to calculate the equilibrium constant. So let's just bring down what we had there. Try and figure out what we started with at equilibrium. Right, so we are told the values at equilibrium for these two. That says at the equilibrium, that's the values that we've got. So this means we can put those two numbers in straight away. So I3 negative is 0.116. That's divided by I2 is 121 times 10 to the minus 3. That's going to be times whatever the iodide is. So within potassium iodide, so the I negative, dealing with that. So at the start equals 0.239. Now we need to know the end at equilibrium. What's the value we've got? If you look at the product, we have made 0.116 moles per litre of the I3 negative. This means that's how much is going to be taken away. So there's a 1-to-1 ratio between all of them. So that means if we've made 0.166 mole, 0.166 of the I3 minus, we have used that quantity of the I minus. This means we've used 0.116. That gives you 0.123. We can then put that in over here. I'm going to type that in and get our answer out. So with these ones, there's two ways of keeping track of what's going on. You can either look at how much of the starting materials are used up, or if you know how much product you make, you can work your way back to how much reactants must have been used. And that's what I've done in this one. Popping this in our calculator, and that gives me an answer of 779. The equilibrium constant will not have any units. We don't want to put any units in for our constant, so it's just 779 as an answer. Next one, we're asked about the arrangements that we have of our bonding pairs and electron pairs. They are saying that they take B, so B is favoured. That's helpful to note. That must mean something about this arrangement must be more stable, because it's all about repulsion and minimizing repulsion. So that would maybe be my first point. Let's do that. So structures depend on minimizing repulsion. Second thing is that a lone pair repels more than a bonding pair. So structure B keeps the lone pairs as far away as possible. Last question, or last parts of the last question, we have a big old diagram talking about different reaction schemes dealing with ethyl benzoate. So ethyl benzoate is an ester. We have our ester link here. We're hydrolyzing an ester link. Okay, what are we asked for this one? First one, skeletal structure for ethyl benzoate. Okay, so first thing I would do is, well, we're already part way there, because we've already got our benzene ring represented like that. So then what we're doing is that each carbon is a point. We want to have our lines going through there. So we're going to come up to that carbon. Oops. Come up to that carbon. We're still going to have our double bond O. Then going to come down to our oxygen. Then I'm going to go along to our carbon. That's the first carbon at the CH2 and down to the second. So we have carbon, carbon, carbon. That's just it. Need to do. So each time we change direction, it's a carbon unless there's another atom there. And that would be your skeletal form of that one. Next one, we're heating under reflux. You're heating under reflux, you use a condenser going vertically. That helps cool any gases that are trying to escape. And that's the point in it. It prevents any reactants from escaping. It allows you to heat it for longer without the risk of losing product. It will cool down everything that tries to go. It prevents vapors, products, reactants, some kind of word from leaving, escaping, prevents. Now I'm actually going to add in the word volatile, so easily evaporated. Volatile reactants from escaping. Next up, part C, name process X. What is happening in process X? We are separating out ethanol, which is an alcohol, and our salt. We've got here sodium benzoate for that one. So we're separating off alcohol. Distillation will be a really good option for that. So you warm them up and then one of them will evaporate first. So there's ethanol, alcohol involved. We're separating off a liquid and we're keeping that liquid. So if evaporation would just drive off the alcohol, which is not what we want to separate them. That's going to be distillation. Help us with that one. Other name for a dehydration reaction. We are removing water. This chemical here is going to be ethene. Got to have a carbon-to-carbon double bond because it's the only way you can make C2H4. So we're making a carbon-to-carbon double bond by removing water. We have got the opposite of an addition reaction. Addition would break the double bond. So the opposite of an addition reaction is an elimination reaction that we've got there. We're looking for the electrophile. Electrophile means likes electrons. If something likes electrons, that means it's going to be positively charged. It'll be the thing that attacks the benzene ring. Let's see what does that. Electrophilic addition reaction. Down here. That's going to then have to be got HBr. We need to decide which of them is going to be attracted to the negative charge. This will be again electronegativity. Bromine has a higher electronegativity than hydrogen. Pretty sure that's the case. Let's double check. Not the easiest two to see because they're so far apart. We have hydrogen up here, bromine sneaking down here. So yeah, bromine has a higher electronegativity. That would be slightly negative. That means that it would be the slightly positive hydrogen that's attracted to the electrons in the double bond. I thought we're over here when I said about the benzene ring, but it is the double bond. There's lots of electrons in it. So therefore, it's going to be our slightly positive hydrogen that is attracted to it. Not entirely sure the best way of describing it, but something about the positively charged hydrogen in the HBr. Next one, impure precipitate of benzoic acid is produced by acidifying the alkaline sodium benzoate solution. We're asked, why is it got to be alkaline? Okay, so there are two equilibriums to take into account. We have our water equilibrium. And we have our one with the sodium benzoate. Might be an easier way to say it in here, in the data booklet. We're dealing with the benzoic acid. They're talking about having benzoate ion. We're dealing with this equilibrium as well. Let me just pop that down. Okay, so we're dealing with these two ones. So the first thing would be, well, the H pluses are going to react. So our benzoate is going to combine with the H3O positive from the water. That will reduce the number of those. With equilibriums, if you remove one of the components from the right hand side here, our equilibrium is going to shift to the right to replace that. As it shifts to the right, we replace the H3O positives, the hydrogens, but we will also have more OH minuses. We'll have an excess of OH minuses. and that makes an alkaline solution. Okay, next one, we're trying to separate an impure precipitate. So precipitate means it's going to be a solid. We're separating a solid from a mixture. Filtration would be the easiest way than that. You could talk about vacuum filtration, make it go faster. You want to separate a solid from a mixture of solutions and liquids, then filtration will work well. Name process Y. What does process Y do? We are purifying, going from impure to pure benzoic acid. Purifying, recrystallization would be a good one when we're dealing with solids. In this question, we're dealing with a mixed melting point analysis. You would use a pure sample of the chemical with your sample, pure sample of benzoic acid. We're going to use those results to check the purity of it. If our sample is pure, it would have the same melting point as the textbook, the reference. It would have the same as the textbook or the reference melting point. If it's impure, you're going to have a lower and wider melting point range. Next question, we're dealing with infrared spectra. We're given a couple of different spectra to look at, and we're asked to identify the spectrum for ethanol. So what I'm going to look at is I'm going to look at each spectrum. I'm going to look for any of the large peaks and try and identify which bond they result from. We have one around about 1700, none in C. Let's check what the 1700 would be. For an alcohol, we're looking for, go down to 1700, dealing with these ones. So that would mean that they cannot be alcohols because they've got the C double bond O, they'll be aldehydes or ketones or carboxylic acids. In C, we have a peak up at this over 3000 range. We do not have a C double bond O, which would be from our 1700. No peak there. That's our kind of explanation that out of the three, the most likely one to be ethanol would be C. It's got ranges which are up in this OH groups, and it also does not have a carbon oxygen double bond. So our answer would be then C, as that brings us to the end of the paper. That's how I would approach each question. Thanks for watching. Goodbye.